Hi guys, we're going to be going over weak base and Kb calculations. This is going to be super similar to how we were doing weak acid. The two main differences is the equation and then how we figure out the ultimate pH at the end. But a lot of it's going to be very similar. So hopefully you can make the connections, which will make it a little bit easier on yourself. So in this case, just keep in mind when we have a weak base under the Brown-Lowry theory, it's going to be accepting a proton from, in this case, water. So just keep that in mind. That's going to be one big difference. And because it's accepting it from water, we're going to have the production of that hydroxide ion in solution. And then there's just some extra kind of setup stuff up top for us to refer to or for you to look at as we're going through this. So in this first question, we have dimethylamine. You're going to see a lot of amines that has that nitrogen in the compound. It has that lone pair, which allows it to kind of attract and ionize that hydrogen from water in order to make the covalent bond. So it gives us the Kb and it asks us for a pH of 1.5 molar of that dimethylamine. So the first thing we want to do is write out the equation like we've been doing for all of these. Just actually figure this out. So I have CH3 and H reacting with water. Okay, and again, it's going to be acting as a base, so the movement of the protons is going from water to our weak base, which then is going to produce hydroxide and our cation, which is going to be the conjugate acid of our weak base. So we can set up an ice table. And same thing as before, we can take water out of it. We were given the initial concentration of our weak base. We can say that our hydroxide is at 0. Similar to the weak acid, there is technically some hydroxide in the solution from the autoionization of water, but it's going to be much less than 5% of the hydroxide from the weak base. So we're just going to start it at 0. And then we have 0 to start of the cation. And then based on the direction that has to proceed towards equilibrium, we know that the reactant side is going to have minus 1x. And then based on the balance equation as well, our products are going to be plus 1x. So we can combine our expressions. Okay. All right, so then from there, we're going to be using the Kb expression. So here we have Kb. We're going to have our products over our weak base, our reactant. Okay, they gave us the Kb, so we're going to have 5.9 times 10 to the negative 4 is equal to x times x, or x squared. And then we have our 1.5 minus x. And just like we were doing with the weak acid, we're going to say that change in x is going to be less than 5% of the original concentration, which we'll show at the end. So I'm going to remove that and simplify the expression. So when you cross multiply and take the square root here, you're going to get x is equal to, keeping to the 2 sig figs, 3.0 times 10 to the negative 2. This is probably the biggest mistake, is students automatically, just out of habit from dealing with weak acids, plug that in and take the negative log of it, thinking that they're getting the pH, when really when they do that, they're getting the pOH, because that x value is actually not equal to hydronium, it's equal to the concentration of hydroxide. So I'm going to go back up and just fill in the rest of my chart. And then for the weak base, you end up getting like 1.47 something. So keeping it like with the 2 sig figs in the 10th place, this ends up staying the same. So this is the other extra step. So once you realize that that x is your hydroxide, we just then need to, you can either find the pOH and then get the pH. I almost always find the hydroxide concentration using the Kw and then plug it in to get our pH. So here I'm going to do my concentration of my hydronium would be equal to the Kw divided by my hydroxide. And that is because when we did the autoionization water, we talked about how the concentration of hydronium is equal, or times, is multiplied by the concentration of hydroxide in order to get our Kw. So then we can go ahead, our Kw for water would be 1 times 10 to the negative 14th. Okay, then we go ahead and plug in our concentration of hydroxide, 3.0 times 10 to the negative 2. When you plug that in, keeping it to 2 sig figs, you get 3.3 times 10 to the negative 13th. Okay, then from there, now that we actually have the concentration of hydronium, we can find the pH, which would be equal to the negative log of that value. Okay, and then keeping with 2 sig figs, you would have 12 point, and remember the sig figs for pH come after the decimal, 12.48. Okay, which makes sense. We have a weak base. We should have a value or a pH greater than 7. So that's one way to check that. One other thing is, because I did make the simplification there, if you do the change in X divided by 1.5, I get about 2%, which is less than the 5%. So that checks off too. So I just want to make sure I go back to that and show that to you. So again, very similar, just have to be careful with the reaction, careful with finding X, understanding that's your concentration of hydroxide, and then correctly solving for hydronium and thus the pH. All right, this would be a good chance for you to pause, try out number 2, and then check over your work, or if you feel confused after this one, then just go ahead and watch it with me. All right, so for number 2, here we have pyridine. You can see that nitrogen there, which indicates you probably have a base involved. It gives us, in this case, the pKb of 8.77, and it asks us for the pH of a 0.1 molar pyridine sample. So I'm going to start with my reaction. So I have my C5H5N. It's going to be reacting with water. Okay, it's going to, again, the hydroxide, or the hydrogen is going to be transferred from the water to the weak base, producing our hydroxide in solution, which is going to give it its basic properties, and then our cation. I feel like I was saying anion before, which I'm sorry about, because it's positive. Your cation, which is your conjugate acid of our weak base. I'm going to set up my ice table, taking and removing the water from that. And then we can go ahead, we start with our 1 molar weak base, again assuming that we're going to have our 0 concentration of hydroxide, and then there is none of the conjugate acid present yet. So then we can go ahead, based on our balanced equation and the fact that it's going to proceed to the right, we can set up our change in concentrations and then express them in terms of what they will be at equilibrium. Okay, and then as you recall from the last one, this is where we're going to need our Kb value. So initially, because we're given our pKb, we're going to do 10 raised to the negative pKb. So 10 raised to the negative 8.77, which, keeping to the 2 sig figs in the pKb, I get 1.7 times 10 to the negative 9. Okay, then I'm just going to set that equal to my products over reactants. So I have X times X over my 0.10 minus X. I'm going to go ahead and simplify that, just like in the previous example, and remember to go back and show the check for that. So when you solve for X here, remember X is going to be your concentration of hydroxide. And keeping to the 2 sig figs, I get 1.3 times 10 to the negative 5. So I'm going to go ahead and just fill that back in up here. And then with this one, I think you get something like 0.0999. So when you round it, you still get your 0.10. Also, I'll do the check right now. When you fill it in, you actually get just 0.013%, which is definitely less than our 5%. So that checks off for validating our assumption there. And then remember, this is where we have to be really cautious, recognizing that that concentration was hydroxide. So I'm going to find the concentration of hydronium in order to get my pH, which is my Kw divided by my hydroxide amount. Kw is 1 times 10 to the negative 14th. Plugging in that concentration of hydroxide, 1.3 times 10 to the negative 5. Oops, sorry about that. And then when I get that, you have 7.7 times 10 to the negative 10, which is my concentration of hydronium. And then I can go ahead and find my pH is equal to my negative log of 7.7 times 10 to the negative 10. And then keeping to the 2 sig figs, I get 9.11 as my pH, which again makes sense. It's greater than 7, which indicates that weak base. One little note is what you may want to do is just, usually they suggest that you round at the very end. So when you get this amount of hydroxide, yes, I'm writing it down as the rounded amount, but you can leave your value in your calculator and walk through the rest of the calculations in order to get to your answer there. So that's one little thing to keep in mind. All right, so go ahead and do the one practice for me, and I'll be giving you practice leading up to the tests on these weak base calculations.